Let's find the theory of everything and break conservation of energy. Best thing, we don't even have to stand up for this, because this equation already rules them all. This principle not only gives us Newton's equation, but also covers electromagnetism and even general relativity. It leads us to why and when energy and momentum are conserved, and it plays an important role in quantum physics. Hi, I'm a physicist, and this is the principle of least action, or rather stationary action, as we'll see. It tells us how every single thing in our universe moves. It covers so much, even though it's a rather simple framework. But in comparison, we don't see it that often in pop science content. That's a shame, because if we combine this formalism with Noether's theorem, we'll actually derive conservation of energy, a concept so important and fundamental that physics teachers nearly slap it in your face. But is conservation of energy really so fundamental? No. Strictly speaking, the energy in our universe is actually not conserved. But before you doubt everything you thought you knew, this is fine. Trust me, we'll get to that. But first, let's discover how everything moves, so we can then understand the principle of least action, which is the closest we've come to a theory of everything. Then we'll see how all of this simply follows when we rewrite it as the Euler-Lagrange equations. To break conservation of energy, we first understand why and under which conditions energy should be conserved in the first place. So we discover Noether's theorem, which actually also gives us conservation of momentum. And in the end, all this tells us something important about how physics actually works. So I'm not gonna leave you like this or this. Okay, we want to find a theory of everything. So it should describe how everything in our universe moves around. That's how we can predict things like when you need to reach out to catch the ball. What do all things in the universe have in common? They are lazy. Or as I like to call it when someone accuses me of being lazy, efficient. If you need to get from one place to another within a certain time, you take the shortest path. That way you sweat the least. That's efficient. A meteor cruising through space is also efficient. It takes a straight path, because that's the shortest path. If I shine a light beam onto your face, the light also takes the shortest possible path. Until I put you into a lake. All for science, of course. Now the light beam bends. Why? One answer is Snell's law. The other answer, or actually kind of the same answer, is light does not take the path with the shortest possible distance, but with the shortest possible time. Light travels more slowly in water, which is why the distance covered in water is smaller. This is faster than this. So in both cases, something gets minimized, either the distance or the time. So all things move efficiently in the sense that something gets minimized. Okay, let's get back to catching the ball. Wait, this does not look like the shortest distance or shortest time. This is supposed to become a theory of every single thing. Well, something is minimized here as well, namely the action. Why is it called action? Because it needs a name. Why is it denoted with S? Because physicists like to confuse people. What is the action? Well, to answer this, let me first introduce another quantity, the so-called Lagrangian. That's again not a very helpful name, but at least this time it's abbreviated with L. The Lagrangian is kinetic energy minus potential energy, denoted by T and V. Yep. Why is there a minus? We'll see. The ball flies from my hand into your hand within a certain time. If we calculate the value of the Lagrangian at every point of that path and add that up, we get the action. Summing over every point is the same as integrating. So the action is the integral over kinetic energy minus potential energy. We integrate from the moment I release the ball until the moment you catch it. The path of our ball minimizes this action. So the number the action has for this path is as small as possible. How do you get a small number? To get a small number, kinetic energy should be as low as possible, and at the same time potential energy high, since potential energy enters with a minus. But if you try to keep kinetic energy very low, the ball cannot travel very high, but then potential energy is also low. This means the optimal path perfectly balances kinetic and potential energy to minimize the action. Mathematically, this minimization is expressed like this. At the minimum of a function, the slope of a function is 0. So that's what delta s equals 0 is supposed to tell us, that the action is minimal. That's why it's called the principle of least action. But actually, the slope of a function is 0 whenever the function is stationary, so when it's minimal or maximal. So the name principle of stationary action is more precise. You can find the stationary points of a function by looking at small variations of it. So you study what happens if you slightly vary the function. This is what Hamilton did to the Lagrangian. Mathematically speaking, he used the variational principle. That's why you also find the name Hamilton's principle, and why this delta is called the variation of the action. Okay, a lot of names telling us that the ball takes the path with minimal action. Actually, it tells us that the paths all things take between 2 points are those with stationary action. The shortest path and the one with shortest time are special cases. But wait, if you want to know the path of something, don't you need an equation that tells us its position? Yes. This brings us to the Euler-Lagrange equations. Let's take a look at the Lagrangian. You probably know that the kinetic energy of something like a ball is given by 1/2 times its mass times its velocity squared. Velocity tells us how the position of something changes. Mathematically speaking, the velocity of something is given by the derivative of its position with respect to time. Physicists often denote this with a dot. Why? Because physicists are lazy, or actually efficient. But then, why did I write the word position instead of a letter like X? Okay, let's write a letter, but then we use the letter Q. Why? Because why not? I can do whatever I want. And because in Lagrangian or Hamiltonian mechanics, we usually use Q for position. I guess due to historical reasons, or again, just to confuse people. So, we put a Q here to indicate that potential energy directly depends on position. Okay, so overall, the Lagrangian depends on position, velocity, and time. If we rewrite the principle of stationary action by moving the variation inside the integral and do some math, we find that all this has to be 0, which is the case if the part in the integral is 0. And that's the Euler-Lagrange equation. To see why this gives us an equation for the position, let's look at the meteor cruising through space. It only has kinetic energy and no potential energy, because it's not in a field. When you do the math, we find that its mass times its acceleration is 0. To spice things up a bit, let's move the meteor closer to Earth. Now, it's in a gravitational field, so it has potential energy. It has the potential to fall towards Earth. Plugging this into the Euler-Lagrange equation, we now find this. Does this look familiar to you? What about now? A force actually tells us how potential energy changes, and it points into the direction of minimal potential energy. That's what the minus is telling us. In Earth's gravitational field, for example, the force of gravity points towards Earth. The closer you are to Earth's center, the smaller your potential energy. Put differently, you have a higher potential to crush your phone's screen if you drop it from a higher height. So, this here is nothing else but the force. Wow, we got Newton's second law out of the Euler-Lagrange equations. That's amazing! We could now integrate this twice to get an equation for the position. You can do this the other way around as well. You can derive the principle of stationary action or the Euler-Lagrange equations starting from Newton's second law. When you do the math, you eventually use this connection between conservative forces and potential energy. And that's the reason for the minus in the Lagrangian. Deriving equations of motions, so equations for the position, velocity or acceleration, out of the Euler-Lagrange equations is especially powerful when things become complicated in Newtonian mechanics. When there are so many forces involved that it's difficult to keep track, we can just look at kinetic minus potential energy instead. And it doesn't stop there. That's the action for meteors, balls and everyday things. But in classical physics, there's an action for everything. There's an action for electrodynamics, and using the Euler-Lagrange equations with this action gives us Maxwell's equations. There's also an action for general relativity, which leads to Einstein's field equations. Isn't that astonishing? That's why this equation rules them all. What about quantum mechanics? Here, no surprise, particles do weird stuff. They kinda take different paths at the same time, and you basically work with probabilities. The probability that a particle goes from one point to another is given by the sum over all possible paths that lead there. Again, this infinite sum is mathematically an integral, a so-called path integral, and that's where the action enters. Okay, now we have a theory of everything, or at least the closest thing we can currently have. Let's proceed with the second step of our plan. Let's break the conservation of energy. To do this, we first need to know why energy should be conserved in the first place. Why does energy stay constant over time? Because of Noether's beautiful theorem. It states that if the action stays minimal under certain transformations, there must be a corresponding quantity that is conserved. What's a transformation? It's applying some kind of mathematical operation onto position, velocity or time, like adding 24 hours to every t. If we throw the ball tomorrow instead of today, what happens to the action? Well, the ball still takes the parabolic path, so the action is still minimal. Now Noether's theorem tells us that there must be a corresponding quantity that stays constant over time. Noether's theorem also tells us how to calculate this quantity out of the Lagrangian. We find that the quantity that corresponds to this shift in time, which we call time translation, is nothing else but energy. And that's why energy is conserved, because the math tells us so. It tells us that if a shift in time keeps the action minimal, energy must be conserved by definition. So, we do not have to assume or state conservation of energy, we can just follow the math. How amazing is that? I told you, you don't have to stand up for this. And Noether's theorem has way more to it. There are more transformations that leave the action minimal, and thus give us a conserved quantity. No matter if I throw a ball from here or 10 meters to the right, it still flies a parabola. This shift in space or space translation tells us that momentum must be conserved. And if the action does not change under angular rotations of the system, we know that angular momentum is conserved. That's Noether's theorem. Let's use it to break conservation of energy. Energy is conserved because we can make a shift in time and the physics stays the same. It doesn't matter when I throw the ball. But what if we zoom out? If we talk about bigger stuff and way longer time periods? You probably know that the universe is expanding and that this expansion is accelerating. So doing something now or an incredibly long time later actually makes a difference. The universe's expansion causes things to drift apart. The situation does indeed change over time, over a very long amount of time. So this does not hold anymore. You probably also heard from the cosmic microwave background, photons from the early universe that we can still observe today. Just that they don't look like our day's photons. They are stretched, because they stretched as the universe expanded. So their wavelength is now bigger, or put differently, their frequency is smaller. The energy of the photon is directly proportional to its frequency, or to 1 over its wavelength. So these photons did lose energy. The energy was not transformed into something else. It actually got lost. The total energy of our universe is, strictly speaking, not conserved, because a large enough shift in time changes things. We say our expanding universe is not symmetric under time translation, so there's no conserved quantity for this transformation. Actually, we did not break conservation of energy, it was just never there. But don't worry, this is fine. Here we looked at billions of years. Humanity is just 300,000 years old. For our purposes, the effects of an expanding universe are so small. Time translation symmetry almost perfectly holds. So it's perfectly fine to approximate that this is true. We can keep slapping the conservation of energy into people's faces. Alright, we've explored this beautiful framework that teaches us how everything follows a path that minimizes a quantity we call action. Does this mean we should stop using other theories? No, this is something you should always keep in mind when talking about theories in physics. This is an important part about how physics actually works. A theory is just one way of describing observed phenomena. It's not reality. It's just a description of certain parts of reality. Similar to a map that does not show us everything but helps us find our way. Different kinds of map highlight different things and are therefore more or less helpful in different situations. Similarly, A particular theory might be more helpful than another in a certain case, but all the concepts and theories we use today are somehow valid. Entropy, for example, is a concept that's helpful in a lot of cases. But unfortunately, it's often misunderstood. If you want to clear your misunderstandings, check out this video. If you learned something new, please leave me a like. Thanks for watching. Have a wonderful day.